Okay, so let's start. Once more, a warm welcome to everybody who joined the webinar. Today's topic will be gas flow measurement with ultrasonics. So today we will talk about the measuring principle. A lot of you already know this principle anyway. I will take this very brief, and then we will talk about the general specification of gas measurements via ultrasonic. Then we go in some more details into the clamp-on technology, advantages and disadvantages. The same for the wetted technology. And after that, we will see typical pricing, so of wetted and clamp-on technology for gases. After that, we will show you some alternative technologies with their advantages and disadvantages, so that at the end of the presentation, you have a decision matrix if you have to decide for a gas measurement, which is the best technology for my application. And for sure, at the end, I'll try to be in time. I think the presentation should be done after approximately 45 minutes. There's plenty of time that you can ask all your questions. Or if you want to, feel free to go into the chat and send any questions to Thomas. Okay, the ultrasonic technology. Most of you will know it. We have a transit time principle, which means here is a pipe, or a symbol for a pipe, and you always need two transducers, one upstream transducer and one downstream transducer. And the ultrasonic transducers, they are working as a loudspeaker and a microphone. So they are sending ultrasonic signals first with the flow and a second shot against the flow. And the signals which are traveling with the flow, they are faster than the signals which are traveling against the flow. And this time difference, if you know the geometry and the angle and everything, is a measure for the flow velocity. So the average flow velocity on the path is length with this very short formula. So, and if you multiply this with the square section of your pipe, or if your duct or whatever, then you get a flow rate in cubic meters per second. There's some calibration values inside for Reynolds compensation or other effects, but the basic formula is that formula. It's the same for liquids, it's the same for gases, so very simple equation. What you see here is something to remember for later. Ultrasonic measurement is a speed or a volumetric measurement, so it's not a mass flow measurement, but it's a volumetric measurement. So if you look into the general specification, what is very good, we have a huge measurement range. So you have a very high velocity. You have a very high velocity range. So even from velocities below a centimeter per second, you already have a measurement. So the resolution is millimeters per second. And you can measure to very high velocities, such as 20 or 30 meters per second in gases. So if you say starting of the measurement is at 1 centimeter and it's going up to 200 meters per second, then we are facing a velocity range which can be measured of 1 to 2000 or something like that. So this is a good thing with ultrasonics. For the clamp-on, the pipe integrity stays untouched. So you put the transducers outside of the pipe, which means no drilling, no cutting of the pipe. If you have a process which you cannot interrupt, it's an ideal solution. If you have toxic or corrosive or whatever fluids, clamp-on technology is untouched by that. So the pressure range of a clamp-on gas measurement, there are some applications where you can start at 4 to 6 bars. 10 to 12 bars is a good start. The higher the pressure, the better for the clamp-on measurement. Why is that the case? The densities of ambient gases, they are so much lower than the densities of the pipe wall. So the step from the pipe wall through the gas, we see this later on with some more details, is very big, and therefore the higher the density, the better for the measurement. So for a clamp-on measurement on a metal pipe, you should have at least 6 bars or something like that. Plastic pipes, which are not very often in industries, you can measure down to ambient pressure. But for steel pipes, you should have approximately 6 bars, better 10 to 12 bars. So our wetted flow meter, which is the delta wave SUF, this is designed from 0 to 16 bars. So there's other manufacturers with wetted technologies where you can measure up to 100 bars, but our flow meter is designed from 0 to 16 bars. Typically for natural gas pipelines, for pressurized air, for combustion air, natural gas for combustion processes, nitrogen, whatever. So in this mid-pressure range, the wetted delta wave is used. The temperature ranges for the clamp-on meters, it's -40 to 160 degrees Celsius. We have high temperature transducers, but they can only be used for high pressure applications. They go up to 350 degrees Celsius. For the wetted ultrasonic meter, we have a temperature range from -25 to 60 degrees Celsius. Accuracy of the clamp-on. A typical accuracy is 1 to 3% of flow, ±2 centimeters per second. For the wetted ultrasonic meter, we have a custody transfer accuracy 0.5 to 1%, ±0.25 centimeters per second, which is an extremely high accuracy. The measured physical unit, as I said before, is speed or volume flow. So it's not a mass flow meter, it's a volumetric flow meter. Condensates is an issue. Be careful with condensation in the pipeline. This might lead to a loss of the signal. Particles, usually, if it's not too much particles, they don't have a negative influence on ultrasonic flow meters. Okay, let's go in more details to the clamp-on flow meter now. So here you can see a typical installation, and the guys of you who have experience with clamp-on liquid measurements, they see that the installation is a little bit more complicated here. So number one is usually you are measuring in set mode, which means you have one transducer on one side and the other transducer on the other side. And you see also here some foils which are close to the transducers. So with a clamp-on flow meter, I can install it in 5 minutes or even less. For a clamp-on flow meter, clamp-on gas flow meter, you need a little bit more time and need to do a better job than for a clamp-on liquid flow meter. Clamp-on liquid flow meter, usually if there is a rusty pipe or something like that, you clean it a little bit, you put the transducers on it. You can measure usually through the paint and everything. This is very easy. For a clamp-on gas meter, you need a little bit more. You need a little bit more work. I show you now why this is the case. So this is once more a principal design of a clamp-on gas measurement. So you have the transducer here. You have the pipe wall. It's here very thick. It doesn't need to be that thick. It's just for better visualization. Then you have the gas. And once more, you go through the pipe wall to the transducer. So now such a transducer is optimized, and you have a very straight signal. So I make here the width of this line shall symbolize the strength of the signal. This is very well, and also we design our transducer that the coupling into the pipe is pretty good. So the first coupling of the acoustic signal is from the transducer into the pipe. You're losing some signal here, but not too much. So this is something which is in our control. Which is out of our control and which is driven by physics, is now the next process, which is the coupling from the steel pipe into the gas. And this is a difficult obstacle. Why is this the case? We call it an impedance jump. So you can imagine if you have a loudspeaker in your room, then you have membranes, and the membranes, they are very soft and they make a big movement to get the sound into your room, so to make it visible. but in a steel pipe, this is not possible. A steel pipe is very hard. It has a high flow velocity, and so the impedance jump between the gas and the steel pipe is very high. So here the problem is that most of the signal is lost here in the coupling of the pipe into the gas, and the rest of the signal is now a very thin line, so we are losing a lot of the signal strength. And here, this is what I told you before, the higher the pressure of the gas, the higher the density of the gas, the better is this coupling here. So if you have a steel pipe at ambient pressure, forget about it. The reflection here will be so much so that the signal which is going into the pipe is not good enough. This is why for steel pipes, typically we ask for 6 to 12 bars minimum pressure to have a good signal in coupling. Now, the problem is we don't have this just once, but we have it twice. So here at this point, we have the next step where we reflect most of the signal. So most of the signal is going back into the pipe, and just a very little part of the signal is going through the pipeline and then into the transducer. Here, the signal is very little, and now we have most of the signals are reflected here and reflected here, and therefore the real signal which is coming to the transducer is very small. And there is another problem. This reflected signals in here, they are also making trouble with the received signal. I show you that with the next pages. So once more, this is why the installation of clamp-on transducers is a little bit more complex as for clamp-on liquids. Once more, for clamp-on liquids, the good thing is that the liquid has not the same density, but a similar density as the pipe. Well, therefore, the impedance jump is much smaller here, and we get much more signal for liquids inside than for gases. So what do we need to do for a clamp-on gas meter? Number one, we need a good and solid placement of the transducers. Therefore, we have these trays or tracks with stainless steel ropes. You have to go directly on the pipe, so sand the pipe, make a good surface, use the coupling compound, and that you have a very good encoupling of the acoustic signal into the pipe. At least where we are in control of the coupling, you should do a good job. In the next step, we put these damping foils on it. We saw on the last screen that we have a lot of reflections, and these reflections, they tend to disturb the signal. So for clamp-on gas, we need these damping foils which damp down the reflected signal, and they do this pretty good. So damping mats is to reduce the reflections. So we have the transducers in here. They are firmly attached to the pipe. There is some coupling compound. We have a good surface, so we have prepared everything very well to have an optimum encoupling of the signal into the steel pipe. This is necessary for clamp-on gas meters. By the way, if you have high pressure applications offshore, 40 bar, 60 bar, 100 bar, or something like that, then it's almost the same as for clamp-on liquids. So then these measures in some cases can be avoided, but for 10 bars, 12 bars, or something like that, this is needed. What happens? So we see here the yellow is the reflections which we don't want to have. We want the damping mats on the pipe, and they lead to a damping of this reflection. So we effectively reduce the dampings. Here is a real life signal before damping mats. So you see how the signal is looking. So the effective signal is in here, and all these things here, these are reflections or ringing of the pipe. And after putting damping mats on it, you see the real signal is looking much better. So these are signals out of the field with and without damping mats. Okay, as I told you before, the clamp-on flow meter is a volumetric flow, as a vortex is, as a turbine is. So a lot of flow meters are volumetric flow meters. So is the ultrasonic. But for some applications, you might like to have a mass flow meter. For that, you need to measure the pressure and the temperature in the pipe. Then you can calculate the density and you can calculate the mass flow. If this is needed, the flow meter has our flow meter has PT100 inputs and analog inputs here on terminal 3 and 5 to integrate a temperature and pressure measurement, which gives you the possibility to calculate the density. Unpleasant fact is if you need to measure the pressure, this is not possible with clamp-on. Temperature you can measure with a clamp-on meter, but for the pressure measurement, for sure you need somewhere a hole in the pipe and a half-inch thread or something like that. So if you want to measure mass flow, you need to have a pressure sensor in the pipe. Okay, this is the cable room of the clamp-on flow meter. This is for the transducer. In this case, it's a dual channel flow meter, channel 1 and channel 2. We have two PT100 inputs. We have one relay for alerts or for counting pulses. We have two analog inputs for pressure or for temperature. We have two analog outputs. We have two pulse outputs. And we have the possibility here to set up any type of digital communication, such as Modbus, Mbus, or whatever. And we have a USB interface for setting up the meter and reading out the data logger. Okay, so let's come and get together some expert tips for clamp-on ultrasonic flow meters. By the way, this is valid not only for Systec flow meters, this is valid for all types of clamp-on flow meters. Basically, they work with the same principle, they have the same issues, so this is good for Systec, the delta wave COG meter, but also for all other types. So number one, the smaller the pressure, the more difficult is the measurement. The higher the pressure, the better is the measurement. For Systec, we can handle steel pipes starting at approximately 6 bars. At 12 bars, usually we don't have a big issue. My advice is if you have a pipe which is below 12 bars, better make a test measurement before. The test measurement might take you 2 hours or something like that, but then you have peace in mind. The higher the pressure, the better the application. So if you have international pipelines with 70 bars or 40 bars or something like that, no problem, it will work perfect. But if you're below 12 to 10 bars, things are getting more and more difficult. Plastic pipes, we can measure at ambient pressure. Thomas, if he goes to trade shows, he always have a model with a plastic pipe where he can show a gas flow measurement with clamp on at ambient pressure. Unfortunately, in industries, we don't see these too often. Very important for clamp-on gas measurements, prepare the pipe perfectly, make a good surface, make damping mats to make sure that you get the optimum encoupling of the ultrasonic signals. For standard mass flow, you need a temperature and pressure measurement. So, and here is a perfect application. This is a natural gas pipeline at 40 bars with very low efforts. You put it on after 1 hour, you have a perfect measurement, which is in line with the turbine. Very nice measurement. So this is the ideal application. Okay, let's go to the SUF, which is the delta wave SUF is our wetted ultrasonic flow meter, which is a very interesting device. But it's wetted, which means you have to cut the pipe and get in the flow meter into the pipe with 2 flanges. So what we have here, we have a flow straightener at the inlet, which means if you have a short inlet, a short straight inlet, this flow straightener will optimize your flow profile. So this is the second part of the flow straightener. So number 1 and number 2, this is a 2-part flow straightener. And then you have 1 to 4 measuring parts. Here for the small diameters, this is a DN32. You have 2 paths. This is 1 path, and this is the other path with wetted transducers. What is the good thing about wetted transducers, the transducer is in direct contact with the fluid, and you can optimize the encoupling membrane to gases. So we don't have this issue going through the pipe wall and something like that. Therefore, it's much more easier to measure with a wetted ultrasonic signal. The good thing with our flow meter, which you don't find too often in the market, we have a pressure and temperature sensor integrated, which means you can measure directly mass flow. So it's volumetric plus standard volume mass flow. And also in the head, we have integrated the flow calculator for standardization. We have also integrated a 5-year battery, which means if you don't have external power supply, the battery will work for 5 years. But you can also for sure connect an external DC power supply. Then the battery will not be unloaded. And there is a number by standard, a number of IOs. So by standard, we have a 4 to 20 milliamp output, which can be just operated with external power. For sure, if you have 20 milliamps, the battery will not last for 5 years. So therefore, the 4 to 20 milliamp is driven by external power. We have a Modbus RS485 integrated. Also needs to be powered by external power. By the internal battery, the pulse output can be driven. So there is a pulse output if you want to have an external counter. This is battery driven. The good thing with this flow meter, it's really unbelievable. So we have a very precise gas test bed at Systec. And this gas bed is with calibrated turbines. The turbine is the big turbine is around 35,000 euro. It's a 0.25 turbine, and the small turbine is a 80 millimeter turbine. And we have to combine both of the turbines to go through the whole flow range of the SUV. So in this case, you can see we have driven the flow meter from 20 centimeters per second up to 30 meters per second, and the accuracy is just astonishing. So this is mass flow accuracy, so including the temperature and pressure calibration. You see the accuracy of span is within 0.23%. So it's just a perfect flow meter for each application, also for test beds. We are just rethinking our test bed if we replace our calibrated. So these are our turbines are calibrated by the highest authority, by the PTB in Germany, and we are thinking about replacing them now by the ultrasonic flow meters because the span is just huge and they just fit the zero line. So with a small calibration here at that point or linearization, and at that point we can come to a just perfect accuracy here. So very impressive. So once more to get the details together, the ultrasonic flow meters are in contact, in wetted contact. Therefore, the impedance drop between the transducer and the gas is optimized, so we don't have a minimum pressure requirement for that. Our flow meter is for 0 to 16 bars. There is competing products, for example, from Elster and from Krone. They have high pressure flow meters for international pipelines, but they are definitely playing in a different league in terms of the pricing. So we are talking here of a factor of 1 to 20 between their pricing and our pricing. So therefore, we are more focusing on the low pressure side. The temperature range, which is compensated, is from -20 to 60. Don't go for condensing fluids. So if you have condensing fluids, put a condenser before. This might cause an issue with and signal loss. It's ideal for air, for natural gas, for combustion air, for nitrogen, oxygen, hydrocarbons, whatever type, in all types of combustion processes. For pressurized air to calculate the pressurized air or whatever. As mentioned, the temperature and pressure measurement is integrated, which is very helpful. And as an output, you get volume flow and standard volume flow. Via Modbus, you get also temperature and pressure and everything, but if you're using the 4 to 20 milliamps, for sure you can get just one physical value outside, which is typically the standard flow. With the Modbus, using the Modbus, you get also pressure and temperature out. The SUF is manufactured in 1-inch DN25 up to DN300, which is 12-inch. 12-inch, yes, it is 12-inch. And the span, the calibrated span is typically 1 to 100, but the flow meter is even starting at lower flows. And if you overflow it by 20%, it's still working. So the calibrated span is 1 to 100. But the effective span is 1 to 300 or even more. So the DN300, for example, it's from 12 cubic meters up to 7,000, which is 1 to 600 or something like that. And the accuracy, the standard is class 1, and optionally you can get it with a class 0.5. By the way, I believe you can calibrate it even to a higher accuracy. It's just that this is the limits that we can give you with our test bed here. There is a battery integrated by standard, and if you don't power it up, it will last for 5 years. But there is a 24 DC input on board, so if you power it, it will the battery will not be discharged. Here you can see a typical application in the field. You need to flange it in, so you need to cut the pipe. This is the disadvantage compared with clamp-on. The design of our meter is pretty much the same as for mechanical flow meters. So typical mechanical flow meters are quantometers or turbines, and the dimension is adapted to their standard sizes. So for the smaller diameters, it's 241 millimeter, I believe, and this exactly fits to standardized turbines for gas applications. So easy replacement. The meter is monkey-proof. Sorry, bad word, but you don't need to set it up at all, so it's completely set up. There is a setup which is usually sealed by us. So we make a seal on the setup to make sure that the calibration values and all is inside there. You can remove the seal and change parameters, but then we don't give you any warranty on the calibration anymore. And the sealing is a preparation for the custody transfer. So we intend to go with the flow meter to custody transfer for natural gas within the next 2 years, which needs quite some efforts here with our test bed and the calibration equipment and everything. So therefore it will need some time, but the flow meter is from the accuracy ready for custody transfer. As I said before, it's autonomous with the battery, short inlet sections due to the flow straightener, which is inside of the meter. Okay, let's come to the expert tips for the SUF. Need to cut the pipe, that's the disadvantage. It's not suitable for condensing fluids, so if you have wet gases, don't use a clamp-on ultrasonic flow meter. This is not only valid for Systec, this is in general valid. The background is because with a liquid surface, you have another impedance jump between the transducer or the pipe to the gas, which gives also reflection. So there's a good chance that you lose your signal if your pipeline is wet. If there from time to time is a drop passing by, it might not be a problem. But if the pipe is wet, if the surface is wet inside, you might have headache. The SUF is designed for mid-pressure rating, so 16 bars typically. It works with short inlet, which is very nice. External pressure and temperature compensation, it's not necessary. It's already integrated. You can operate it by battery, which is also good. Okay, now I tell you a little bit about the pricing of clamp-on technology and SUF, and afterwards we go through through competing technologies with their advantages and disadvantages. So if you have a portable clamp on measurement, the pricing structure, the electronic with all the equipment, all the accessories is approximately 7,500 euros, and the transducer is between 2,500 and 5,000 euro, depending what size you need. So a measurement starts at approximately 1,000 euro. Once more, for the guys from you who have good experience with clamp on liquids, this is more complicated and takes you a little bit more time. So it's not a 5 minutes measurement. You need the damping mats and everything. Also with the clamp on technology, it will take you 1 hour or 2 hours to get a measurement. But anyway, if you have a turbine in the field, or if you have to replace a turbine or to calibrate a turbine, you can install a portable clamp on flow meter as a for the time being when your master flow meter, for example, is in calibration. Ideal application. The portable meter has analog and digital output, so it can replace installed flow meter for the time being if it's for calibration or repair, for example, or you can test meters. So very interesting technology for companies like natural gas suppliers or something like that. They usually have those meters to check in the field or to replace their meter whilst calibration. So for a fixed meter, for a fixed installation, the hardware, including the transducers, the price is approximately 7,500 euro. The installation for a clamp on flow meter is 1 hour, commissioning 1 hour, or let's say 2 hours or something like that. So the total cost of ownership, also important for clamp on technology. There is no wear and tear, there is no drift or something like that. So in general, you do not need to recalibrate it compared to mechanical flow meters, which need to be recalibrated. The total cost of ownership is not so high. So 7,800 euro for a flow meter might sound more expensive than for other flow meters, but if you compare it with flow meters where you have to cut the pipe and which you have to replace for calibration and so on, the total cost of ownership is not so high. So it's 7,800 euro, depending on the pipe size, let's say up to 9,000 euro. Now with the SUF, this is really price-wise a very attractive technology. So we made really a low-cost flow meter with a perfect accuracy. So the hardware cost for a DN50, for example, is 3,200 euro. This includes temperature and pressure compensation, the flow calculator, everything. Installation for sure is a little bit longer, so it will take you 8 hours, for example, to cut the pipe and everything. Commissioning 1 hour, so let's assume 900 euro. So the total cost of ownership is 4,150 euro. For custody transfer, we are also try to get a recalibration interval from the PDB of 5 years, which means also the total cost of ownership for 5 years is 4,100 euro, which is very attractive if you have a process where you have the possibility to shut down the process and install the meter. Okay, that's it basically about the ultrasonic flow meters. I now want to show you in the next approximately 10 minutes some competitive technologies. The first is DP measurement. Most of you know we are one of the world market leaders with pitot tubes, but there is also beside pitot tubes, orifices, venturi, so these standard elements. So what is the advantages of DP measurement, DP-based measurement? You have by far the biggest pressure and temperature range. So you can use DP meters for basically 200, 500, 1000 bars, whatever temperature ranges. Our pitot tube is used up to 1200 degrees Celsius. So you hardly can beat this with other technology than DP meters. It's very robust, even if there is normal soiling, normal condensation. In particular, our delta flow pitot tubes, they are very robust. You have a good accuracy between 1% and 3% approximately. The recalibration needs to be done, but just of the pressure and temperature sensors, which you can easily remove and recalibrate them locally on site within minutes, so recalibration is inexpensive and easy to do. And for pitot tubes, the installation is very easy. So for a pitot tube, you just need a 1-inch stud and you install it in the pipe. For venturi, for sure, on orifice, you have to cut the pipe, and depending on the dimensions, it takes more time and more money for the installation. Disadvantage, you don't have the high flow range of a ultrasonic flow meter. So typically for DP meters 1 to 5, maximum 1 to 10 is the standard. With the delta flow, if it's perfectly designed and you use 2 differential pressure transducers, you can go up to 1 to 20. You need a pressure and temperature compensation. So you have a certain pressure loss. For a pitot tube, it's very low. For orifice, it might be very high, and the pressure loss might be also expensive. From the hygienic aspect, so measuring beverages is not possible because you have dead volumes here. And the installation for venturis or something like that is pretty expensive because you have big dimensions and you need to cut the pipe. Vortex, the same is true for swirl flow meters or something like that. Advantage, they are pretty robust against normal soiling. They have also a good accuracy, 1 to 3%, and you can use it as the DP measurement for gases, for steam, for liquids. This is also for DP measurements. Disadvantage, it's also wetted technology. It's not very well suitable for vibrations or pulsations because the vortex is in the region of machine vibration. So if you have machine vibration and pulsations, these meters might be disoriented. For recalibration, you need to remove the complete meter, which is sometimes not so easy, and it's more expensive. And typically vortexes are produced up to DN 250, so not for big diameters. For natural gas, a typical technology is still these turbines, these massive turbines. Advantage, they have a perfect accuracy, so you can go to 0.25 as the turbines in our test bed. So they are used for custody transfer meters, very accurate. Disadvantage, only for low temperatures. It's a wetted technology once more. They are extremely sensitive to dirt and liquids, so don't use these moving parts for dirty fluids. They will be destroyed very fast, and it's not suitable for vibrations and pulsations. And the recalibration, once more, you need to remove the whole flow meter. Pricing-wise, 10 times of our ultrasonic flow of our SUF ultrasonic flow meters. So a turbine, a calibrated turbine, DN 200, 25,000, 30,000 euros, something like that. There is a cheaper version which are called quantometers. They have an accuracy of 1 to 2%. Same technology, but with less calibration and less accuracy. You can get those for example, approximately 6,000 to 8,000 euros. Without temperature and pressure compensation. So this is also a volumetric meter. So if you want to compensate to standard conditions, then you also need temperature and pressure compensation. Okay, widely used flow meter are thermal flow meters. Easy installation, similar to a pitot tube, just a 1-inch or whatever stud, you can install it. The good thing of thermal mass flow meters, it's a direct mass flow measurement. This is nice. They have a big flow range, so you can measure a centimeter per second up to 20 meters per second. And they are cheap. It's depending on the brand you are using and the quality. So for example, this ABB flow meter is a high-class flow meter. You come in the range 6,000 to 15,000 euros, so not cheap. But there is, let's say, for heat and ventilation purposes, also thermal mass flow meters, which might be below 1,000 euros. So the span is big of the pricing. But these meters, they are tricky. So number one, it's a single point measurement usually. So you are measuring in one point, which means if you want to have a good accuracy in the very long straight inlet. ABB, for example, they sell these meters also together with a flow straightener. and with a filter in before to get them to a better accuracy. Then they are getting much more expensive and also have pressure losses if you have flow straightener and filters. Wetted technology, that's clear, and that's the main devil. They are very sensitive to dirt and condensations. So a lot of people use them, for example, for pressurized air, and they have a compressor, and the compressor is claimed to be oil-free. But oil-free of a compressor means there is not too much oil, but after half a year, if you go with the finger inside the pipe, your finger will be black. And this is making a tremendous drift off on these flow meters. So if you have surface condensates or oil or dust, then they are drifting like hell. So after a year, you might see a deviation of 10 to 15% before the calibration. So be careful if you don't have very clear fluids. So they are also not suitable for pulsations. So we know this from engine test beds where Systec is doing a lot of work. So if there's pulsation coming back from the engine, the readings are not correct. And you need short recalibration intervals, in particular if you have not perfectly clear gas. Thermal flow meters, from my point of view, for process industries, be careful. If you are, for example, in medicine, and if you have bottled gases or something like that, thermal mass flow meters are good technology to use. But if you're measuring pressurized gas, if you want to measure combustion air and it's not filtered air and you have a rest of oil or soil or something like that, don't go for thermal mass flow meters. In the automotive industries, they are widely used as a reference flow meter for engine test beds. Recalibration interval in the automotive industries is between 3 and 12 months. So they recalibrate them. On good test beds, they recalibrate them within 3 months. So all 3 months, they ship them back to the manufacturer and put a second one in, which is pretty expensive. Okay, let's see if we compare the prices under the economic conditions. An orifice with pressure and temperature compensation, hardware, we are talking about small flow meters, 80 to 100 millimeter, might be 7,000 euro, installation 1,000, and the calibration over 5 years is 1,000. So total cost of ownership for 5 years, 9,000 euro. A quantometer, this is a cheap turbine, as I said before. Hardware with pressure and temperature compensation, 10 to 12,000. Installation 1,000. Usually they have a calibration interval of 5 years, so no extra calibration for 5 years. So total cost of ownership 11,000. Vortex with no pressure and temperature compensation. If you're just going for a volumetric flow meter, total cost of ownership 3,800. That's a good deal. Similar to a delta wave SUF. Vortex with temperature and pressure compensation. You need a temperature and pressure element, 1,000 euro. You need a flow computer, 2,000 euro. Cabling and everything, installation 1,000 euro. So then you are facing total cost of ownership 7 to 10,000 euro. So then you are at least as expensive as a clamp-on flow meter, or as expensive, much more expensive than the SUF. So thermal flow meter, the price range is very big, as I said before, from 500 euro to 15,000 euro. So this is really depending what type of flow meter you are using. If you have a high quality, it's much higher than 2,000, but installation is easy. Maintenance and calibration, depending on your application, depending on your accuracy needs, but total cost of ownership is also in the region of a wetted flow meter from Systec. Our Delta Flow DF25, the pitot tube, together with our multi-variable transmitter. So you have already a mass flow meter here. There the total cost is approximately 6,500 euro. Installation is very easy. Maintenance and calibration, once you have to calibrate perhaps the DP transmitter, total cost of ownership 6,000 to 8,000 euro approximately. As I promised before, so I'm pretty good in time, so I'm proud about myself. I said 45 minutes, and we are ready with the presentation and ready for your questions. Here is a decision matrix if you go for a flow meter. So here's what you might look for, and here's the different technologies. I don't go through this matrix. You get the presentation, and you can use this to get to a fast idea what the cost is of that. So